Welcome back. So we have been looking at recurrence relations and how to solve recurrence relations using generating functions. So to quickly recap, so recurrence relations is basically a sequence of numbers where the initial set of numbers are given and the nth term of the sequence is given as a function of the previous terms. Now, recurrence relations is used extensively in various subjects. We have seen how recurrence relations can be used to model counting problems and how one can try to solve recurrence relations. So there have been some of the examples that we looked at, and for some of them we have managed to give you ideas how to solve them. So the first idea was been to guess the solution and then prove by induction. Now, of course, if you can guess the solution, then proving by induction is a very simple technique. But the main question is, how do you guess the solution? The technique one that was given to you was that you can unfold the definitions and that might help you to guess the solution. We saw some of the examples of that. But then there are some problems. For example, this one, which is the Fibonacci number, where guessing the solution is pretty complicated. And one of the reasons to believe that it is complicated is that the actual formula of Fn will come out to be this number, which is something that's of course scary enough, and hence one don't expect to guess this such a formula by itself. The other one is if the formula has something like this floor or ceiling or some kind of stuff like that, in which there doesn't exist any nice guesses. But in the second case, one can use or one can prove some upper bound and lower bound, and that might be good enough for us. And in fact, we can use the asymptotic notations of big O, big omega, theta, small omega, small o, and sim to come up with asymptotic expressions for these sequences, which is possibly good enough. For example, one way of going about this example is you first guess the mn for some n, which is some good n. For example, here we saw that we can guess it for n equals to power of 2, and then here mn does become something like n log n, and you prove that mn equals to theta of n log n, and you do it by proving by using induction to prove an upper bound and a lower bound separately. Now, this is good if the formula again has some nice expression for some particular n. We saw some master theorem which kind of helps us to identify the formula or guess the formula when the expression is of a particular kind. But what do we do when we have a formula like this? f0 equals to 0, f1 equals to 1, so f0 equals to 1, f1 equals to 1, and fn equals to fn minus 1 plus fn minus 2. Now, when it is of this kind, problem is that there is no easy way to guess it. How do you guess fn? Even getting an upper bound and lower bound which is close tight enough is not an easy job. For example, this is the particular expression of this fn, and it clearly shows that even getting a proper or theta notation for this fn is not an easy job. Instead, what we can do is that we talked about a new technique which is called generating functions. The main idea is that consider sequence. So in this case, you can think of the f0, f1, f2 till f infinity. Now, once you have been given the sequence of numbers, you can consider the polynomial P of x equals to a0 plus a1x plus a2x square and so on. So in other words, P of x is summation of an x power n. Right? Now this is a polynomial. And here, this is called the generating function for the sequence a0, a1 to a infinity. Now, so I have done nothing. I have converted the generating function into a polynomial. Now, if somehow I can compute the coefficient of x power n in this polynomial, I will get a formula for the an, because an is the coefficient of x power n in the polynomial px. Now let's see what's going on here, or how do we get the formula for p for the coefficient of x power n. So before that, we might have to use some of the Taylor expansion. In the last class we saw that we can use the generalized binomial theorem to get some Taylor expansion for some of the functions like 1 plus x power minus 1 or 1 plus x 1 minus x power minus 1 and so on. And we will be needing it in due course for this thing. Now let's see how do we use the formula for this expansion. Say this is a simple one. We start with the simple one, and slowly we will handle the more and more difficult recurrences. So this is a simple recurrence. A0 equals to 2, A1 equals to 3 times An minus 1. So if I write the polynomial P of x as A0 plus A1x plus A2x square plus A3x cube and so on, then since I know for all n greater than or equal to 1, I can write it as an equals to 3 an minus 1. So I can write a1 as 3 times a0, a2 as 3 times a1, a3 as 3 times a2 and so on. Which is, now let's look at this first one. So this is a0, and now if I take the 3x common, what do I get? I get 3x times a0 plus a1x plus a2x squared plus and so on, right? So this is of course the polynomial that we are looking at. So I get a0 plus 3x times px. So in fact what I am doing is that I am writing the polynomial in an equation where I am using the given recurrence to write this one, right? So this is very crucial. So I first write down the polynomial and then I write the polynomial using recurrence but using some nice trick. So by doing so, I get a formula. There, namely, I can take this minus 3x px in the right hand side. I get 1 minus 3x times px is equals to a0, right? Or in other words, px equals to a0, which is in this case 2 by 1 minus 3x. So px was some polynomial which was written abstractly using the recurrence or the sequence a0 to a infinity. But now I have written px as a polynomial that doesn't have anything to do with the recurrence any longer. Now, remember this Taylor expansion that we did? We had 1 minus ax whole power minus 1 is 1 plus ax plus a square x square plus a cube x cube and so on. So by putting the value of 3x here, what do I get? So we get that, so this is 1 minus x, 3x power minus 1, right? 1 by this one. So it is 2, which is this 2, and 1 by 1 minus 3x is 1 plus 3x plus 3 square x square plus 3 cube x cube and so on. Right? You can see that here I have used the Taylor series expansion of 1 minus 3x power minus 1. And by doing so, I now know what is the coefficient of x power n. Here the coefficient of x power 3 is 3 power 3 cube, coefficient of x square is 3 square, so coefficient of x power n is 3 power n. So in other words, coefficient of x power n is 3 power n times this 2, which is 2 times 3 power n. And hence this helps us to solve the whole recurrence relation. So we have used an abstract form known as the generating functions for first writing a polynomial, then trying to use the recurrence to get an equation for the polynomial, and then writing the polynomial using some Taylor series expansion, which helps us to identify the nth coefficient, which is my desired thing that I want to do. Right? So we will see how to write it down formally once. So in formal proof, we have this one. So the p of x is summation of an x power n. So px is equals to a0 plus n is greater than or equals to 1. In that case I get an, which is 3 times an minus 1. This is where I have used the recurrence relation, which means I can take 3n out, 3x out, so I get a0 plus 3x into summation an minus 1 x power n minus 1, n is greater than 1. Now I can change the base for this sum, so since n is greater than 1 and this I have both n minus 1 and n minus x minus 1, so that means this is exactly n equals to 0 an x power n, which means this one is polynomial. So this is of the same a0 plus 3x times px. And so we have 1 minus 3x equals to px times a0. That means px equals to 2 by 1 minus 3x. And by Taylor series expansion, we can see that the px equals to 2 times 3 power n x power n, which means an equals to 2 times 3 power n. So this is the formal proof for solving this recurrence relation an equals to 3n minus 1. Now this is not a recurrence relation. So I mean, you could have solved this recurrence relation in some other way. There are different ways of solving this recurrence relation. But I wanted to use this recurrence relation to show you how generating functions can be used to solving it. In the next 2 video lectures, we will see how this generating function technique can be used to solve way more complicated recurrence relations. So in fact, in the next video we will see another example, which is the Tower of Hanoi example. How can we solve the Tower of Hanoi example? And in the video after that, we will see how we can solve the Fibonacci series expansion. In the meantime, if you want to try out, please try out your hand on using generating function technique to solve these 2 things. Thank you.